So we were doing, not yesterday, Monday, we were doing change of variable stuff. And at the end, I had set up a region for you, and we were debating what changes of variables might be a reasonable thing to try. So I'll put that picture up again, if I can remember to do it. So we had xy equals 1, xy equals 3. We had two hyperbolas. We then had, to make life interesting, a straight line and a parabola. Y equals 2x squared. And the region we were looking at was this region in here. And so, say, evaluate, for example, the integral of xy over the region S. So you guys had nominated some different possible changes of variables for us to look at. For example, I think we all agreed that putting u equals xy would be a good idea to make these curves look simpler. But there was some debate about what to use for our second variable. So y over x was one option. What were other things you guys wanted to try?
X over y. And then one person said x squared over y. But
Did somebody say x squared over y?
they did, but I didn't think of. I personally disagree with that option.
Was it you?
No, it wasn't me. We can look at the tape.
You could even try just something like y or x or something, I suppose. All right, so let's fiddle around with it and see what happens. So remember that this is all, again, doing it backwards from the setup of the theorem. The theorem, recall, refers to starting in the UV plane and mapping by some change of variables so that you have some region here. And the problem here by composition gets turned into an integral over the region back here. And whenever we're writing down the change of variables this way, we're of course working with the inverse. Now, you might ask yourself, is this an invertible change of variables? In other words, is this a one-to-one function that sends xy to uv and a one-to-one function that would send uv back to xy? So there is something to worry about, which I will come back to. Worry, question mark. Are we working with one-to-one maps here? So for example, if I tell you the product of two numbers and I tell you the quotient, do you know the two numbers?
It could be, especially for xy, you could have, doesn't really matter which one's which.
Well,
Not if
correct,
zero.
but this one ought to distinguish.
Not if one of them is 0, if y is 0.
Okay, zero's bad.
But we don't have to do
Good.
anything in zero.
Yeah, because then you could just make one a function of the other and plug it in.
Yeah, we don't have to
Or
worry
if
about
it's like
zero.
y over x equals 2.
Well, what can you do to x and y that will keep the product the same and keep the quotient the same?
Multiply it into
Greater than 1?
Multiplying by 1 did not do anything, Davis.
1. I know, but it kept them the same.
Adding zero.
Absolute value.
Close. So,
Squaring.
no, I want to keep the product the same and keep the quotient the same, but change x and y individually. Take negative of both.
What's the part, like, what would be the
Well, I'm warning you that you may not have a one-to-one function here. But in the region you're interested in, you won't have a problem saying, if I restrict to where x and y are positive, then I have a one-to-one mapping. Okay, so I'll come back and mention that a bit later. So let's just plow forward here. So let's try this one first. So u equals xy, v equals y over x. Can you actually figure out the inverse function here?
So we want x and y in terms of u and v?
Can you actually solve?
You can solve for one and plug in.
Okay, so you think you can solve?
Possible. Maybe not me personally.
Well, I hope so.
And so,
Can you combine u and v and get y? What can you do with u and v that would give you y?
Well, y is
square root of
Yeah.
x times v.
Right. Y is the square root of uv, right? If you multiply these two things, the x's cancel, you get y squared. Assuming y is positive now, you see where I was, right? Y is the plus or minus the square root, and assuming y is positive, then we take the square root. What about x?
It's the square root of v over v.
Again, assuming x is positive, right? Okay, so we have g. Not very pretty, perhaps. Wish the physics major in the room would damp my blackboard for me. This is like an exercise in simple harmonic motion here. Okay, what do we do? So we have several steps to do, right? We have to write down, we have to do the derivative matrix, take the determinant, and that's our fudge factor. But we also have to figure out
The function
and
and the limits.
The
of
region.
the region. We have to figure out the region. So what do you want to do first?
U.
U goes from 1 to 3.
All right. So the integral of xy dA over s is going to be the integral over our region omega, yet to be determined, of what's xy in the new coordinates?
U.
U. And then I need to take absolute value of the determinant of dg, and then I integrate with respect to u and v, and I set it up as an iterated integral once I know what my region is. All right, so what's dg? Good review for you guys.
So whatever
There
the
might
first
be more
one
room than that.
is
Let's do u, du, and what?
So I'm taking the derivative of this with respect to
U.
Like
Over
negative
1/2
1/2.
u
It's-
v.
it's 1/2 the square root of 1 of uv.
1/2.
1 over 2b.
That's what it's.
derivative of u to the 1/2 is 1/2 u to the negative 1/2, and the v is a constant, so it sits there. What's the partial respect to v?
1/2 root v over u.
Of the top line,
Yeah.
that'd be
Oh.
negative,
This is
negative 1/2.
Root u over
v to the
e to the
negative
well, 3 over 2 on top.
Okay, so I'm mixing notations here in a not very pretty way using a square root and a fractional power.
Wait, is there a reason?
No. I just don't want to write over square root of v cubed.
But then you put it all in one.
All right,
Okay.
now to the second line.
1/2 root v over u.
1/2 square root of v over u, Daniel says. And then this one symmetrically. Okay. Gold star if you can take the determinant correctly.
So yeah.
1, 4, 4v minus, or maybe plus, that would be 1/4, 1/4 v squared.
1/4.
I'm sorry, 1/4 v, yeah.
Everybody agree? You've got a v to the 1/2 in the numerator, a v to the 3/2 in the denominator. That leaves a v to the 2/2 in the denominator, which is 1/v. So this isn't so bad. Although, this wasn't much fun. Okay, so what do we get? Integral of u times 1/2v. Now I need absolute values here in principle, so let me just put it there so you get in the habit of not forgetting it. Absolute value of 1/2v, and then I have to integrate over my region. All right. So what's our region going to be?
U goes from 1 to 3.
Just a question of backtrack, where did you get integral of xy? You just,
I just made that
oh,
up.
you just made it up, okay.
Good question. All right, so u starts at 1 and goes to 3. Okay. Now what?
He has v equals 1.
This is v equals 1, right?
Yeah. And then v equals basically 2u. 2x.
Scratch work. So what's Reese doing here?
So. if
How do
you
we
take-
figure out what the orange curve becomes?
Well, I was just going to divide an x over to the other side, which would be v, so that equals 2x. I guess it's not
So you
really
said
useful.
y over x. Yeah, what is that? Does that help?
No, not really.
But can you do like u over v? U divided by v?
U divided by v,
Yeah.
that would be x squared.
And 2 times 2u over v.
So notice we actually have done the hard work already.
Okay, so yeah, it's 2u over v.
So you could just substitute in y equals 2x squared. Right? Since we already had done this, why not just use it? So what does this simplify to?
Do we want to put it in some like v equals something of u?
I'll settle for anything at the moment, and then we'll figure that out. How do we simplify
Both
this?
sides
V
times
to the
v
3
and then
halves
divide by
equals
root
2
u.
root u.
So v root v over time equals 2u over root u. So yeah, that'd be v to the 3 halves.
Okay, so if I want to work with that curve in a nice way, what should I do?
Put in calculators. And then v equals,
Square.
Square both sides, right? So assuming I'm working where everybody's positive still, I get
v equals 2u 1/3.
Do we agree?
Mhm.
4u is v cubed. So how do I graph that?
Can't use like v equals 4u over v squared.
That's not
U
good.
equals v cubed over 4, correct?
Yeah, can we see?
You just
U equals v cubed over 4. All right, so
Flip it in your head.
so v equals u cubed would go this way. U equals v cubed goes this way. So roughly speaking, it goes like this.
So 4.
So when u is 1, v is bigger than 1, right? So this is 4u equals v cubed. And so what's my region going to be? It's obviously going to be that. Okay? So how do you want to set this up as an iterated integral?
I would do u on the outside.
du, yeah.
du dv.
So can we agree that we're in the portion where both u and v are positive, so I'm going to get rid of the absolute value sign and write u over v here. Now, you mean you're saying what? du dv, is that what everybody wants?
No.
dv dv.
Yeah, if I do,
I want to hold you.
If you do du dv, you do two integrals, don't you?
right, if I do v on the outside, I'm gonna have to break it into two pieces. So you're fired.
Can I be hired because I do that?
No.
Please? Can I get your spot now?
All right. U goes from, that was easy. For fixed U, let's not forget our routines here.
From 1 to
1
cube root
to
of 4u.
Extra set.
Cube root of 4u. 4u to the 1/3 power here in the top. Okay. Oh, this is looking yucky.
Is it though?
Let's see how many people can actually finish the problem.
Would it be better to do the two integrals so you don't have to deal with like a one up, so you can do u first since it's on top, I believe.
I don't know. I'm okay with doing this.
Should the one with the yellow absolute value mark, should that be over omega?
Oh, thank you. All right, so integral of 1/2. What's the integral of v dv?
UL.
Except I write log because we're a math class, not an engineering class.
Use cursive.
V goes from 1 to the cube root of 4u.
This would actually like be better, wouldn't it?
So
Because
that's
1/3 will come out.
Right. So I have 1/2 u. What's the log of the 1/3 power of somebody?
1/3
log.
So I get 1/3 log of u minus log of 1.
1/3 log of 4u.
All right, be picky. Minus u log of 1. So I'm left with this. How many people remember how to integrate u log u? By parts.
We factor out the 1/3.
You can factor out the 1/3. And what else can I do to make life slightly easier?
You can just add +4 log
That's log 4.
I could break log of 4u into a sum of logs. So now, this is easy. How do I integrate u log u? You may have already said that.
This one thing just memorize.
No. So those of you who have been lazy about thinking about how you do integrals, maybe this is a time where you can actually practice some.
Can we use x and y here? Because like integration by parts with u and v, with u's and v's is very confusing.
So I've got 1/6. Let's do the integral that's easy. Log 4 times u squared over 2. So what's the u squared over 2 going to give me? Minus. No, don't do that.
4.
Say here,
4.
9 minus 1 is 8 over 2 is 4. And then I have plus 1/6 the integral of u log u. And so Jonathan has memorized integration by parts with the letter u, and that's confusing him.
X equals log u.
So remember, integration by parts is doing the product rule backwards. Which function do I want to make simpler by differentiating? So that should be the one we differentiate, and then what the other one is the one that we have the derivative of. And integration by parts is going to tell me that the integral of f times the derivative of g is fg.
Minus integral g.
So what's g?
1 v squared.
And what's f prime g?
1 over u.
Squared over 2.
So f prime is 1 over u, g is u squared over 2, so I have u over 2. And this is evaluated from 1 to 3. This is integrated from 1 to 3. And this is the last integral I'm going to beat to death today in here. Okay, but I just want you to believe we can actually finish the problem here. 9 over 6 is 3 over 2, so I have 3/4 log 3 minus, what happens when I plug in 1?
That's 0.
Zero.
And then I have to subtract the integral of u over 2, so that's u squared over 2. We've done that before, right? That's 4, and that's the answer. Pretty amazing mess, isn't it? 2/3 log 4 plus 3/4 log 3 minus 1/3. Of course, I knew that answer right when I started.
If we do d to dd, it will be easy. You know, it's like you have a square and then you have only one integral from.
Well, the logs will have to come from somewhere.
Wait.
We did it right.
I mean, you know
Well,
there's
it's
going to be
true.
logs, and you knew that you have this function, x, y, v1, x, y, v2.
I knew what?
You didn't have logs.
I did? Really?
I didn't.
I didn't.
You have something kind of weird.
All right, let's try a different change of variables. I'm not going to persist to the end working it all out, but let's set it up. You guys, what's different? Oh. Before I do a new way, before another change of variables, I have a comment here, and I'm going to pursue this comment. Could we have done the problem without explicitly solving for g?
Doesn't all we really need the determinant of g?
If we had a formula relating the derivative matrix of G inverse and G.
Well, in fact, do we?
Yeah.
No.
If you knew, we know we had the function g inverse, which we started with, right? U was xy, v was y over x. Those formulas don't look so scary. Suppose you blithely computed the derivative of this function. What would you get?
Y, there's y, 2y with x. And then negative y over x squared.
And then blithely we took the determinant of that. What would we have?
2y over
Y over x plus y over x is 2y over x. Does that look at all familiar?
It's the inverse of
Y over x? That's 2v. To v or not to v?
That's not the question.
It's the,
Yeah, so 1
that's the
over
determinant of dg inverse, so
Well,
Turn
we don't know
dg
whether
would
it
be-
is non-single. I mean,
Well,
Isn't the fact that the determinant's non-zero?
I mean, again, if we're away from y equals 0 or v equals 0, we're okay. So what, is this coincidence or is it not
So
coincidence?
this is
not
the
coincidence.
determinant.
You're
G
taking
G,
the
G
time.
inverse is the
Sorry.
identity. G inverse is the identity and take determinants.
No, you have to do derivatives. What word should you be mumbling?
Chain rule.
Chain rule. So we'll talk more about this in chapter 6, but in the meantime, you guys do remember the chain rule. If I take g inverse composed with g, I get the derivative of the identity function. And what's the derivative of the identity function? The identity as a linear map, right? So I'll write an I for identity. Chain rule says derivative of a composition is so what does this say? The determinant of this times the determinant of this is so is that what we actually just did here? We said take the determinant of dg inverse and evaluate at g of u. In other words, rewrite it in uv coordinates. That's what I did here. And we should get 1 over the determinant of dg at u. Well, that's what we got. So this calculation was a lot easier than all that.
It has absolute value?
Well, you need absolute values to go into the change of variables theorem, but this is just a statement about determinants. So this would have shortcutted all that horrendous algebra that we did here, and I'm foreshadowing here for a situation that will also show up in web work, where maybe we actually have to do this. Now, could I have gotten away without this completely? Well, how did we get the equation of the orange curve? We cheated and we used this. You would have somehow needed, just using these equations, you would have somehow needed to turn this equation into a UV equation.
But we didn't need to do that.
We didn't need to do that. And you might have been able to finagle this and get to this equation without explicitly ever doing that. But again, as Jackson's saying, we wouldn't have had to do this partial derivative stuff.
So when we were finding the determinant of g inverse, we really found it in terms of x and y and then substituted in u and v at the end.
Which is exactly what the chain rule says to do. Take the derivative and evaluate at g of u. In other words, take x and y and write them in terms of u and v.
Okay.
So that's exactly what the chain rule says. Okay? All right, let's try another. I don't want to do too many more because I have another example to do. So pick which one you want to do next. Is x over y going to be that much different? Yes, Jonathan.
If we take the g inverse of x and y and plug in the values of x and y for the y equals 2x squared, don't we get the equation?
Yes.
Now you say x equals xy and y equals y for x.
Wait. You're confusing me.
For y equals 2x squared.
Right. So you would plug in.
For x.
So you would say g inverse of the point. So y is 2x squared. So you would put in. Yeah, this is good. You would get x times 2x squared, and then you would get y over x. You would get 2x cubed, and you would get 2x, and you would ask yourself, what equation in u and v relates those? So that is the right way to do this if you don't want to go through the way we did it. So do you see that it works? If you cube v, you get 8x cubed, which is 4u. Okay? All right.
So why should we make why should we make like a first quadrant assumption?
You didn't have to. So if I had wanted to be, remember Cameron answered my question finally and said we could replace them each by negative themselves. We could have done the same picture in the third quadrant and parameterized this region by a different function g that went from the third quadrant. But we're more used to working with positive things than trying to keep track of everybody being negative. Right? Yeah, you had a choice. That was my point about the original function was not one-to-one, but we make a choice of a restricted domain to make it be one-to-one. And we'll be discussing next week a lot more about how you look at questions about inverse functions and differentiability and stuff like that. All right, I don't want to do x over y because it's really the same thing.
Yeah.
Do we see any preference for y over x for our? So if we still stuck with xy, but then do we see a preference for using y versus x? Well, maybe x would be better just because y equals 2x squared is the equation of the orange curve. So what would happen if I use this change of variables?
What happened?
Well, then x is v and y is u over v.
So now we can easily write down the mapping G without much horrendous algebra. X is v, as Daniel said, and y is u over x, which is u over v. And so now what do we get from the derivative? 0, 1, 1 over v, negative u over v squared. And so what's the determinant?
Negative 1 over v.
Ah, now you have to worry about sign. So derivative is negative, the determinant is negative 1 over v, so I now do need to pay attention to the absolute values.
What if we had just taken the derivative with respect to b first?
Then I have to write vu instead of uv. And that's a valid thing to worry about. But okay, now what is my domain omega going to look like now? Well, u is still going from 1 to 3. And now what about the other two curves? What does the y equal x line do?
Because v equals y. Or,
So Jonathan's idea might be a good way for you to think about it.
V squared equals u.
If you put in y equals x, you have u equals
x squared. So u
x
is v
squared, and v equals x, so u equals
v squared.
v squared. And what about y equals 2x squared?
Y equals 2v squared.
So then you'd have u equals 2
V to the third, right?
v cubed.
Yeah.
And so you would have a region that looks a little nastier maybe, but still natural enough to set it up doing dv du, right? So what would we have? Our integral would become u goes from 1 to 3. Our function we're integrating is xy. That's still u. The fudge factor is absolute value, remember, 1 over v, so we have u over v still, without a 2. U over v, and then v goes from,
V squared
be careful,
square root
square root of u
to
to cube root of u over 2. So we're going to get logs again, right? Just like we did before, and you're going to play the same game with the powers coming out as coefficients. Okay, I'm done with this. Any questions?
Why can't we just get rid of the absolute value marks?
I didn't.
Well,
I took the absolute value negative of a positive
Okay.
number and said it was a positive
okay, I
number.
get it now. So,
V is almost.
Okay? Okay, here's a question now. Here's an example for you guys. That's going to be a little more off the beaten track. So, here's your challenge. I'm going to draw two weird curves here. I'm going to draw x to the fourth plus y to the fourth equals 1. So that's a circle that's trying to turn into a square. I don't know if some of you have thought about this before. But if you put higher exponents on the equation of a circle, it becomes more and more turning into a square in the limit. And then I'm going to do the same curve, x to the fourth plus y to the fourth equals 2. So that's part of my delineation of my region.
Wait, so x to the infinity plus y to the infinity equals 1.
Well,
The
it
limit
doesn't
is
literally make
The
sense.
limit is that we move infinity of x to the equals y to the equals 1.
If you take the limit of the graphs of those functions, it's going to turn you into a square. Yeah. So if you've never thought about that, it's sort of cute to play with. All right, y equals x again. And what? I mean, this is so boring. Let's make it more interesting. This is a hyperbola, x squared minus y squared equals 1.
And does that intersect the x-axis with?
So this meets this curve at the point 1, 1, 0.
Okay.
And of course, this is the region I'm interested in. A common everyday shape that shows up in everybody's calculus course. All right, so here's the integral I want you to do. Evaluate the integral over S of xy times x to the fourth minus y to the fourth.
It seems pretty well constructed.
So are those points on top of each other though, it looks like?
Where here?
That point and the other intersection?
Oh.
At the top.
You meant,
I think they should be.
so this point is at 1, 1.
Yeah, so they are.
Yeah.
So would it be that bad to just
Do it.
do it?
Okay. Defeats the purpose of my problem here.
That's the goal.
So Ken's going to do it in Cartesian coordinates. The rest of us are going to try to be clever with the change of coordinates.
Or you could just change instead of x.
So what-
Just
what-
make it y equals 2, make
X.
it 3.
No.
What would be some natural u and v to try?
The fourth plus y.
X to the fourth plus y to the
And
fourth.
x squared plus y.
How's that going to help this?
How about like x to the fourth be 1 and y to the fourth be another?
I would do x squared and y squared before I did y to the. One of them should be.
Yeah, I like y.
You guys are resisting the obvious substitutions.
Like,
X squared.
X to the fourth plus y to the fourth.
E equals x, D equals y.
Y squared, yeah.
That's what it is.
Yep, Dennis, go ahead and do that. That would be really helpful. I want to try to straighten out as many of the curves as I can. Now, what's going to come up while we do this is, how are we ever going to get the function to work? Right? So right when I start doing this, you're mystified and you think you might be up a creek without a paddle, and you might be right. But Gabe did say that looks well constructed. Maybe the person that made the problem up had something up his or her sleeve. Now, here's why I had this whole discussion. Can you actually solve for the inverse function? Assume you're in a region where there is an inverse function. Can you tell me what x and y are in terms of u and v?
I don't know.
I mean, I can't. Can you? So you don't want to, right? So the question here is, can we get through this problem without ever explicitly figuring out G? Well, skip it, but then we have to do this going around the backdoor approach, right?
So it'd be like,
So if I consider G inverse again of x and y,
x squared minus y squared.
then what is the derivative matrix of G inverse?
2x negative 2y. 4x to the third. 4y.
Right.
2x,
2x,
negative 2y.
negative 2y.
4x to the third. 4y.
So what's the determinant going to be? And I recommend that you actually pull out the 2 and the 4, remembering to use properties of determinant. Well, that's harder, actually. You need to pull out an x for this column and a y for this column. Is that what you want me to do? All right. And then what am I left with? I'm left with 1, negative 1, x squared, y squared. Or you could just do it without being so clever. So what am I left with? 8xy, x squared plus y squared. Now, isn't that interesting? xy, xy.
So if we multiply x squared plus y squared times x squared minus y squared, we're going to get.
X is worth minus y, it's worth.
So what happens here?
Then it becomes 1 over 8xy that, and then.
So remember, right, you need, for the change of variables, which I've now erased, you need absolute value of the determinant of dg, which is 1 over this. And you're supposed to write it in terms of u's and v's.
Fortunately, we're going to get like
Why don't we go ahead and
So-
mix it
So
with
if we take f times 1 over determinant of dg inverse, what do we have? We have
x, let's see, 1/8. Yeah. So x squared minus y squared.
over 8.
And then you finally say, oh, but I need to write it in terms of u's and v's. Oh, but that's easy. So I couldn't do all that stuff in terms of u and v, but when I simplify the ratio, I have something I can do easily in terms of u and v. So in uv coordinates, our integrand becomes, what is it, u over 8? That's pretty easy.
I gotta find a region.
Yeah, now we got to find the region. So we write down our original problem, integrating over s is the integral over some hence to be determined omega, 1/8 of u, integrated over uv space. So what's omega?
Well, we know V goes from
So I have to color code now this. What are my colors? They're all very similar. They probably don't even show up. Okay. Okay. So what do we got?
V goes from 1 to 2.
V goes from 1 to 2. Okay. What's y equals x?
It's u is 0.
It's u equals 0. So the line y equals x becomes the v-axis, or at least the positive part of it, maybe. Yeah, v is always positive. So this is what I get. Sorry, the colors are not. I should have used more interesting colors here. And now the pièce de résistance. What's the last curve? Oh, u equals 1. That was boring. Well, that's totally boring. So my region omega is just a silly square.
We should change
What
the
a
problem.
bummer.
I mean, how anticlimactic can you get? Do we need to debate whether we want to do du dv or dv du?
No.
No, we don't really need to. 1/8 the integral of u dv du. Yeah, fine, you can do it your way. 0 to 1, 1 to 2. And even you guys can do this in your head.
Whoa.
You just get u again, right?
Can you skip to them on
Would it
page
be
16?
1/2? So no, it'd be 1/16. Did my head wrong?
Okay, so have fun with web work. Pay attention to not make silly mistakes. Think about what substitutions are intelligent. Set up regions carefully. And if you actually make enough progress that you have some questions, I'll answer some on Friday. Otherwise, I'm going to talk about the proof on Friday
The proof of.
of the change of variables theorem.